Hello, everyone. Welcome back to this lecture series on failure theories. We are trying to find the normal stress and tangential stress on inclined plane of a rectangular member. There you could see the rectangular member. I can zoom this up a little bit. So this is the rectangular member that we are interested in. Particularly, we are interested in computing the normal stress and the tangential stress on an inclined plane of this rectangular member. You could see the inclined plane, the black line that I have drawn. And this particular rectangular member is subjected to a set of normal stresses, and it is also accompanied by shear stresses that you could see that. Now, why we are interested in finding the normal stress and the tangential stress on this inclined plane? Why is that? The reason is it helps us to take some very smart engineering decision. Once you know the value of the normal stress and once you know the value of the tangential stress, it helps us to take engineering decisions. If you're a structural engineer and if you're a mechanical engineer, you should be interested in failure theories. All right, particularly, I think if I have to say this with its very precise shade of meaning, I have to say that particularly we are interested in finding what is the maximum normal stress and what is the maximum tangential stress. What I mean by tangential stress is the shear stress. That is what I am interested in. Because if I know the value of the maximum normal stress and if I know the value of the maximum shear stress, then I will be able to know whether that particular material, whether it is a ductile material or a brittle material, depending on the type of the material, I'll be able to tell whether this particular material is able to withstand the maximum normal stress that is produced on a specific inclined plane, right? And the maximum tangential stress that is produced on a specific inclined plane. And the maximum normal stress and the maximum tangential stress occurs on a specific plane. It's not all the planes. That's quite obvious. It occurs on a very specific plane. Okay. So last class, we derived the expression for the maximum normal stress, a general expression for the maximum normal stress, and the expression for the tangential stress. So using this particular expression, you can just shift the values of theta, and for any plane you can find what is the maximum normal stress and what is the tangential stress. Not the maximum, but you can actually find what is the normal stress and what is the tangential stress that is acting on any plane just by using this expression. Okay, and you can see the top expression there. You can see the yellow lines, the yellow highlighted region, and you could also see the blue highlighted region. The yellow highlighted region indicates the normal stress, the contribution of the normal stress acting on this rectangular member. The blue highlighted region explains the contribution of the shear component, shear stress, tau, that is acting on the rectangular member. Okay, so obviously if tau is equal to 0, then you will be left out with only the contribution by the normal components. In exactly the same manner, you could also see the contribution by the normal stress and the contribution by the shear stress on this rectangular member. Then you could see that for the tangential stress also. Now, what we are interested in now is finding the maximum normal stress. So how do you do that? There are two ways by which you can actually find the maximum normal stress. One way is by using the concept of maxima and minima. Once you differentiate this particular equation with respect to theta and equate it to 0, because the angle at which it becomes 0, right? That is the angle, that is a plane that carries the maximum normal stress. So once you know the value of the theta, where d sigma divided by d theta becomes 0, that value of theta, when you plug it here, is going to give you the expression for the maximum normal stress. The second way to find the expression for the maximum normal stress is by equating the shear stress expression to 0. Because the plane that carries the maximum normal stress carries the zero shear stress. Okay, so I will just do the second technique. I'm just going to equate the shear stress to zero because the plane that carries the maximum normal stress is called as the principal plane, and the principal plane has zero shear stress. So all I'm going to do is I just equate the shear stress equation to zero. So that's what I have done here, that you could see that when you equate this particular expression, shear stress, and when you equate it to zero, right, here we go, you can take this term and you can throw it to the right hand side. So that's what I have done here, that you could see. Okay, so sigma 1 minus sigma 2 divided by 2 into sine 2 theta is equal to, well, I have thrown that term to the right hand side, so there is a negative sign there. Next, I'm just going to divide the left hand side and the right hand side by cos 2 theta. So if you divide the left hand side by cos 2 theta and the right hand side by cos 2 theta, so you get tan 2 theta. So that's the expression here. You get tan 2 theta, and throw every other term on the right hand side, so you get the final expression for tan 2 theta. Okay, so the final expression for tan 2 theta after mathematically rearranging is 2 tau divided by sigma 2 minus sigma 1. Okay, so what is tan theta in general? Whether it is tan theta or tan 2 theta or tan alpha, tan beta, the formula for tan 2 theta or tan theta is just opposite by hypotenuse. So now we know what is the, did I say opposite by hypotenuse? Terrible mistake. It's opposite by adjacent, right? So tan 2 theta is opposite side divided by adjacent side. So definitely this should be the opposite side, the one that I am shading by yellow. And this should be the adjacent side, okay? So opposite side is 2 tau as rightly marked here, that is the opposite side, and this is the adjacent side. Okay, so this enables us to find what is the hypotenuse. Hypotenuse squared is opposite squared plus adjacent squared, so that enables you to find out what is the hypotenuse side. It's simply 2 tau whole squared, as its hypotenuse is equal to square root of 2 tau whole square plus sigma 2 minus sigma 1 whole square. So since we also know the hypotenuse side, which is square root of, okay, so sigma 2 minus sigma 1 the whole square plus 2 into tau the whole square. Since we know the hypotenuse side, it enables us to define what is sine 2 theta and what is cos 2 theta. Why is that matter? Why does that matter? Because we have the cos 2 theta term here, and we also have the sine 2 theta term here. We just have to substitute the expression for sine 2 theta and the expression for cos 2 theta obtained from the plane that carries zero shear stress. That is interesting. So these two expressions for sine 2 theta and cos theta are taken or derived from by equating the shear stress to zero, which means that is the angle of sine 2 theta, that is the expression for sine 2 theta, and that is the specific expression for cos 2 theta, which when you substitute it here in the expression for the normal stress should give you the expression for the maximum normal stress. Because of the maximum normal stress, the value of the shear is going to be zero. So since sine 2 theta and cos 2 theta are obtained by equating the shear to zero, so it's I think that explains the concept really well. So go ahead and substitute the expression for the sine 2 theta, which is opposite by hypotenuse. So that is the expression here. All right. And also find the expression for the cos 2 theta, which is adjacent by hypotenuse. That is here. Okay, you got the expression for the sine 2 theta and cos 2 theta. All you have to do is go ahead and substitute them in this equation, the first star equation. Okay, so this is what you will be getting. Of course, one thing that we have to notice is there is a plus or minus sign that we have to follow. because when you find the hypotenuse side, I think when you find the hypotenuse side, there is going to be a plus or minus sign here. So first, what we will do is we will substitute the negative, and we will get one expression, and then we will substitute the positive, and then we will get the other expression, which means basically you should get two values for the normal stresses and two values for the maximum shear stress, two values for the maximum normal stress. So that's what we are going to do. So first substitute, you can see that there is a negative here that I'm putting a circle, and there is taken the negative inside cos 2 theta. So sigma 2 minus sigma 1 becomes sigma 1 minus sigma 2. Okay. So expression for sine 2 theta and cos 2 theta by substituting the negative of the diagonal, right? So that gives us, okay, so that gives us this particular expression. So I am substituting the sine 2 theta. Here is our sine 2 theta term, and that is taken here from here, okay. Oh, I'm sorry, that is our cos 2 theta term, my mistake. So I'll do this one more time. So that circle is our cos 2 theta term. So let me mark that by red. So that is our cos 2 theta term. Mathematics is just like moving objects. Take the value of cos 2 theta and substitute it here. And this is our sine 2 theta term multiplied with this tau. Already there is a negative sign, and negative and negative gives us this positive. And when you substitute sine 2 theta, it just gives you this expression here. Okay. So take a minute, allow the concept to sink in naturally in your mind. Just take a few seconds and just peruse the calculations. Okay, fine. I hope the calculations are clear. So now in the next step, what you do is you find the expression for the maximum normal stress. Okay, so just find the expression for the maximum normal stress by substituting sine 2 theta and cos 2 theta values. Of course, I have taken the diagonal negative sign. Okay, so final expression is after simplification, right, is here. So how do we get this particular expression? The final expression is here, that you could see the final expression. Well, if you want a mathematical explanation, sigma 1 plus sigma 2 divided by 2, that is written as it is. And sigma 1 minus sigma 2 into sigma 1 minus sigma 2 is sigma 1 minus sigma 2 the whole square plus 2 tau squared divided by 2 into square root of sigma 1 minus sigma 2 the whole square plus 2 tau squared. So in the next step, what they have done is they have simply multiplied this term, or if I have to be even more precise, I can say this term, say it is A. A can be written as root of A into root A, right? So it can be written as root of sigma 1 minus sigma 2 the whole square plus 2 tau the whole square into square root of sigma 1 minus sigma 2 the whole square plus 2 into tau the whole square. So that's it. So you can cancel this and this. So you'll be left out with only this term. That is what is written here. Okay. So that explains. The next step, they have simply taken the 2 inside the root. So if you take the 2 inside the root, it's 2 square. So 2 square in the numerator and the 2 square in the denominator cancels out. So that gives us this term. So that's the expression for the maximum normal stress. Okay. And in exactly the same manner, you can get the expression for the minimum, minor normal stress. The first one can be called as the major normal stress, and the second one can be called as the minor normal stress. It's called as the major principal stress and the minor principal stress. So just by taking the positive value of the diagonal, so you can just get this particular expression for the minor principal stress. So in summary, you can just simply write it as plus or minus. So plus for the major normal stress and minus for the minor normal stress. Okay. So how do you find the maximum shear stress? So the place where the shear stress becomes maximum, at that place, okay, just assuming if just following the concept of maxima and minima, so differentiating sigma t with respect to theta, and that should become 0. Okay, so that's the trick that we have used to just differentiate them and equate it to 0. Okay, so if you differentiate sine to theta, it becomes cos to theta. Of course, that 2 theta, if you differentiate one more time, you get 2. So that comes outside. And differentiation of cos to theta is minus sine to theta. Of course, there is a 2 that comes in front and equated to 0. And after simplification, you just you take all these terms to the right hand side. You get divide by cos to theta here. You get tan to theta is equal to sigma 1 minus sigma 2 divided by 2 tau. So that is the plane. That gives us the plane at which, this expression gives us the plane that carries the maximum tangential stress. All right. This is the plane that carries the maximum tangential stress. Okay. So all you have to do is, again, represent this tan to theta as opposite side by adjacent side. Find out the diagonal, plus or minus sign is there. So find out what is sine to theta or cos to theta, because those two terms are demanded in the shear stress equation. You can see that sine to theta term is demanded and cos to theta term is demanded. So once you know the expression for the sine to theta and cos to theta, substitute it back in this expression here. Okay, substitute it back in this expression here for sine to theta and cos to theta from the triangle there. Opposite by hypotenuse, this expression, and also this particular expression, which when you substitute it there, you get this expression here. Okay, so after simplification is easy. So you just follow exactly the same procedure. Take the LCM. It's of the form A can be written as root A into root A. So root A in the numerator and the root A in the denominator, they cancel each other out. So that is the expression for the maximum shear stress. Okay. Well, you can also find the plane that carries the maximum normal stress and also the plane that carries the maximum shear stress. Here is the expression for the plane that carries the maximum shear stress. Okay. So you differentiate shear and equate it to 0. So that gives you the expression for the plane that carries the maximum shear stress. And you can also find the plane that carries the maximum normal stress. In exactly the same manner, you just have to differentiate this equation and equate it to 0 in order to get the expression for the plane that carries the maximum normal stress. You can just try it through at your leisure. Okay. So what do we do with this? So this is called, these two expressions, this expression particularly is the maximum principal stress theory. Okay. So when you're doing analysis in ANSYS, you will have an option, particularly if it is a two-dimensional analysis, the maximum principal stress theory may be used. Okay. So that is the expression for the maximum principal stress. Okay. So once you know the value of sigma 1, sigma 2 and the shear stress, you can just plug those values in this expression, turn the crank of mathematics, you will be getting the maximum principal stress. And this is the expression for the maximum shear stress. Okay, so this is the expression for the maximum shear stress. Okay. So you can find out the plane, not only the plane, but also the magnitude of the maximum normal stress and the magnitude of the maximum shear stress. Say, just an example, say for example, you are doing analysis of the wall of a dam. Okay, so in finite element analysis, this comes under the category of plane strain condition, where you will be analyzing only the cross-section of the wall of the dam, not the whole wall. There you could see that you will only be analyzing this section, and you will be dividing that wall into many small. Say for example, triangular elements. It can be a constant strain triangular element or a linear strain triangular element, your wish. And say, for example, you take one triangle, and when you do the finite element analysis, what is the result that you will be getting? You will be getting sigma x, sigma y, and tau. What do you do with this? What you do with this is, now you can take this value of sigma x, sigma y, and tau, and where will you substitute? You will be substituting it in the expression that we derived, which is this expression, where sigma 1 can be treated as sigma x, and the sigma 2 can be sigma y. Okay, and of course you got the tau. So you can find out what is the maximum shear stress that is produced on this particular triangular element, on a specific single triangular element. And you can also find what is the maximum normal stress that is produced on a specific single triangular element, and that is the expression. Here we go. So you can find out, so you can treat this as sigma x, sigma y, sigma x, sigma y, okay? And you can just find out what is the maximum normal stress that is produced. And usually ductile materials, they may fail due to shear, so you can apply the maximum shear stress theory, and you can also check the maximum normal stress, the major principal stress, maximum principal stress theory. So you can find out basically what is the maximum normal stress and the maximum shear stress produced in each and every triangle. Okay, even in fact you can just find out what is the expression for the yes, you can find out in each and every triangle that you can find out. Need not just be triangle. If you want to find out for a quadrilateral element, that's perfectly fine. You can just do that. Okay, so you can see that after doing the finite element analysis, the theory of failure, which is the maximum principal stress theory and the maximum shear stress theory, how it comes in handy. You could see that here. Okay. In the next video, I'm going to introduce you to the concept of magic matrix. Magic matrix is the word that I am using. It is actually eigenvalues and eigenvector problem. So whatever we have derived today, and there is one more way to derive it, and that is the crucial method. That method is very, very important, very crucial. Okay, so in order to understand the next method, in which I will be deriving exactly the same expression, but by using a different mathematics, by using the concept of eigenvalues and eigenvectors, I'm going to use it. And why I'm going to derive by using that method in the next video, in the next class we are going to do that, because when the when the state of stress becomes very complicated, say for example, it is just a two-dimensional member subjected to sigma 1, sigma 2. What if it is a three-dimensional member subjected to sigma 1, sigma 2, sigma 3, and also the shear stress is acting on all the planes? Then the scenario becomes very complicated. So we have to derive by the next method, which is an interesting method. It's a concept of magic matrix that I used to call. So the next video will be on magic matrix. Enough for today. So thank you all for your patience. Much appreciated.